Right now, as you watch this, approximately 100,000 commercial flights are airborne simultaneously over the surface of the Earth. Each one is moving at between 800 and 1,000 kilometers per hour. Each one is separated from the nearest aircraft by rules that allow a minimum of 300 meters vertically and 9 kilometers horizontally in most controlled airspace. The system that maintains those separations, that tracks every aircraft, issues every clearance, manages every transition between every piece of airspace, is called air traffic management, and parts of it are running on computers first installed in the 1960s. Not upgraded, not emulated, running. The United States FAA's en route radar processing systems, the backbone of American air traffic control, used IBM 9020 mainframe computers as their primary processing platform from the 1960s through the early 2000s. The replacement system, called NextGen, was announced in 2007. It was supposed to be complete by 2025. In 2024, the FAA's own Inspector General reported that NextGen will not be complete before 2030 at the earliest, and that critical components remain on schedule that would allow the existing legacy systems to fail catastrophically before the replacement is ready to take over. The system keeping 100,000 aircraft from colliding today has a documented replacement gap, and we are flying through it right now.
To understand why this matters, you need to understand what air traffic management actually does every second of every day. At any given moment, a single en route controller may be responsible for between 10 and 20 aircraft simultaneously, each one at a different altitude, heading, and speed, each one transitioning through their sector in approximately 10 to 20 minutes, while new aircraft enter the sector as others depart. The controller must maintain legal separation between all of them, anticipate when conflicts will occur before they develop, issue clearances with enough lead time for crews to execute them, communicate with adjacent sectors about handoffs, manage emergencies as they arise, and coordinate with military airspace and weather deviations simultaneously. This is done with radar displays, voice radio communication, flight strip systems, some of which are still paper, and a primary radar technology that works by measuring the time delay of radio pulses bouncing off aircraft. The radar technology is called primary surveillance radar. It was developed in World War II. It works by sending a radio pulse and measuring the time it takes to reflect back from an aircraft. The fundamental principle, the physics underlying the most critical component of the system tracking every aircraft you have ever flown on, is 70-year-old technology that the military stopped using as its primary aircraft tracking method decades ago. ADS-B, the GPS-based position reporting system described in a previous episode, was intended to replace primary radar. But in 2024, approximately 30% of the global commercial fleet is still not fully ADS-B equipped, and ADS-B, as discussed, is vulnerable to spoofing. The backup for ADS-B failure is primary radar. The backup for primary radar failure is secondary surveillance radar. The backup for everything failing is separation by time and procedure, the method used over oceans where no radar coverage exists. The system has backups. The backups have backups. But the primary systems are aging faster than the backups are being upgraded.
The most dangerous documented failure in the air traffic management system did not come from aging hardware. It came from software. On September 14, 2004, a software error in the Los Angeles Air Route Traffic Control Center, one of the largest ATC facilities in the United States, caused the center's computers to simultaneously lose 800 flight plans. Not display them incorrectly, lose them. For approximately 1 hour, controllers at one of the world's busiest air traffic control centers were managing aircraft with no computer-generated flight plan data. They reverted to manual procedures, strips of paper, voice coordination, the methods developed before computers existed. No aircraft collided, no passengers were injured. But for 1 hour, in the airspace above one of the world's largest cities, the most complex real-time coordination system ever built was operating on the methods of 1955. 4 years later, on August 11, 2008, A software error at the Eurocontrol Network Manager triggered a cascade failure that affected air traffic management across multiple European countries simultaneously. Over 400 flights were delayed or canceled. Dozens of sectors had to reduce their acceptance rates, meaning they could physically accept fewer aircraft than normal for several hours while the system recovered. Then, on April 5, 2023, a technical failure at the FAA's NOTAM system, the Notice to Air Mission system that distributes critical safety information to flight crews, caused a nationwide ground stop of all departing U.S. flights for approximately 90 minutes. The cause was a database file that had been accidentally deleted during routine maintenance. One file, accidentally deleted, ground stop, every departure in the United States. The three incidents share a pattern. Highly sophisticated systems with extensively documented redundancy, failing in ways that the redundancy was not designed to handle, reverting to manual operations that worked, but revealed each time how thin the margin is between controlled airspace and uncontrolled chaos.
The United States and Europe are not the only jurisdictions racing to modernize their air traffic management systems. China has been building an entirely new national air traffic management infrastructure from scratch, not upgrading legacy systems, but designing new facilities, new radar networks, new communication infrastructure, and new procedural frameworks to handle a commercial aviation market that is projected to become the largest in the world by passenger volume before 2040. China's Civil Aviation Administration completed its first performance-based navigation implementation nationwide ahead of schedule, a milestone the FAA's NextGen program has partially missed on its original timeline. The geopolitical dimension of air traffic management modernization is rarely discussed publicly, but it is present in every ICAO technical committee meeting and every bilateral air service agreement. The country that controls the most advanced and reliable air traffic management infrastructure controls, in a meaningful sense, the commercial aviation that flows through its airspace. When China becomes the world's largest aviation market and manages that traffic with infrastructure newer and more capable than the systems managing North Atlantic or transatlantic corridors, the center of gravity of global air traffic management shifts accordingly. The race to modernize air traffic management is not just a safety program. It is a geopolitical competition that determines which nations will physically control the infrastructure of global aviation for the next 50 years. And the United States, which invented the modern air traffic management system, is currently running behind a timeline it set for itself.
There is a specific scenario that aviation safety researchers call the correlated failure event, a failure mode in which a single technical problem affects multiple redundant systems simultaneously, because those systems share a common dependency that was not identified when the redundancy was designed. The January 2023 NOTAM failure was a correlated failure event. Every redundant process for managing the NOTAM system depended on the database being intact. When the database file was deleted, every layer of redundancy failed simultaneously because none of them had been designed to function without the database. Aviation safety engineers are currently analyzing how many other systems in the global air traffic management infrastructure share this characteristic. A redundancy design that appears robust until the specific scenario that invalidates all of it simultaneously actually occurs. The answer they are finding is not reassuring. The interconnection of systems, radar, ADS-B, communication networks, flight plan processing, NOTAM distribution, weather data integration, has grown faster than the redundancy design has been updated to reflect. Systems that were independent when they were designed 30 years ago are now deeply interdependent, because the integration that made them more efficient also made them collectively vulnerable in ways that were not in the original design specification. The good news, and there is genuine good news, is that the aviation safety community has identified these vulnerabilities before a catastrophic correlated failure has occurred. The near misses, the ground stops, the temporary system failures that have occurred, each one was a data point that has been analyzed, understood, and used to drive the next iteration of system design. Aviation has always learned from its failures before its failures become catastrophic. The question, the one that keeps air traffic management engineers working on timelines they know are optimistic,
is whether the rate of learning is staying ahead of the rate of risk accumulation as the system grows more complex, more interconnected, and more dependent on aging infrastructure that was never designed for the environment it now operates in. The system works. Every flight you take proves it, 100,000 times per day. But the margin between works and doesn't work is maintained by people who know exactly how thin it is and are working every day to make it thicker. Follow for more about the infrastructure keeping the sky safe and the problems it has not yet finished solving.